Continuing our talk on polar covalent bonding, we know that covalent bonding, which is the sharing of electrons between unlike atoms, atoms that are just unique from one another, results in unequal sharing of the electron pair. One atom will be able to pull the electrons in the bond closer to its side, the more electronegative element. The end of the bond that has a larger electron density then ends up to have a net negative region. The electron that is not as strong, the atom that is not as strong and therefore has its electron being pulled away, ends up to have a net positive. And we just showed those symbols as partially positive and partially negative in regions of our molecule. So the term polar covalent bond is referring to an electron pair that is being shared unevenly in a covalent bond. So that results in bond polarity. The actual bond polarity has a symbol shown with a little positive end towards the more electronegative element. The partial negative charge ends up to have the larger electron density, and the partial positive sign is given to the electron deficient atom. So thinking about our water molecule, shown here with its bent geometry, water, we said, has a polar region on top of the negative oxygen, the two partial positives on the hydrogens, the bond polarity itself being represented by an arrow with a little positive sign. And I think that's actually what was being shown in our next examples. If we have an HF molecule, hydrofluoric or hydrogen fluoride, the electronegativity number on hydrogen we can look up in our chart as value 2.1. Fluorine, in which all of the electronegativities are based, has an even 4.0. If I subtract the two, 4.0 minus 2.1, we get a number of 1.9. An electronegativity difference of 1.9 shows a very strong polar covalent bond, where the hydrogen on this side ends up with a partial positive. The fluorine on this side has a partial negative. And if you are viewing this in a colored PowerPoint, you can definitely see the region that is red having more electron density on the fluorine as compared to the hydrogen. Showing that HF is indeed a polar molecule, we can see that those molecules line up in an electric field with the hydrogen ends and the fluorine ends aligning opposite to the charge on those fields. So if this is a plate that carries a negative, we're going to see the hydrogens that are carrying a partial positive line up towards that side. And if we see fluorine who's carrying a negative, you see that larger molecule lining up towards the positive plate in this electrical field, knowing that opposites attract. Most bonds have some degree of sharing and some degree of ion formation to them. And we classify as covalent if the amount of electron transfer is insufficient for the materials to display the classic properties of ionic compounds. Are they solids at room temperature? Do they form three-dimensional crystal arrays? Do they have high melting points? Are they poor conductors of electricity? If the sharing is unequal enough to produce a dipole in the bond, a dipole, just to review, a region that has both a positive and negative, such as a bar magnet, is an example of a dipole structure. The bond is classified as polar covalent, an unequal sharing of electrons. And that happens if we have an electronegativity difference between those two atoms. Electronegativity we defined as the ability of an atom to attract bonding electrons to itself. Electronegativity is in our chart in our text, and it really is just a basis of fluorine being 4. Electronegativity for fluorine is the strongest nonmetal pulling electrons towards itself. The periodic trends show an increase across a period from left to right. More toward fluorine, the stronger it is. It decreases as you go down a group, top to bottom. So the farther you are away from fluorine, the less electronegativity you are. So if this is just a general sketch of our periodic table and fluorine is at the top right, electronegativity increases as you point toward fluorine, and it will decrease as you point away towards fluorine. So that general trend of low to high electronegativity. Fluorine is the most electronegative element high up here. Francium would be the least electronegative, low down here. Noble gases, of course, are not assigned values simply because they're not going to bond with anything, and if they don't bond, it wouldn't make sense to talk about a polar covalent bond with a noble gas. The larger the difference in electronegativity, the more polar the bond. When we subtracted a moment ago HF, we found an electronegativity value of 1.9, a very polar covalent bond, with the negative end toward the more electronegative element. 4.0 was the assignment there on fluorine, very high electronegativity value, therefore we know it will contain the partial negative charge. So high up on the right side, very electronegative, very high values. Low values at the bottom left of our chart. This is a chart right out of our textbook, the trends in electronegativity. So literally I can look up the value for every element. I don't have to memorize those. Fluorine with 4.0, francium with 0.7, the opposite ends of the charge. And this is just showing us that very periodic trend that we drew. Decreases as you go down, increases as you go across. Aim towards fluorine to find the high electronegativity values. If the difference in electronegativity between bottom atoms is exactly 0, it's said to be a pure covalent bond, equal sharing. So for example, a fluorine bonded to a fluorine, 4 minus 4 gives me an exact 0. It would be a pure covalent bond. Two like atoms will always have a pure covalent bond simply because we're subtracting the same number. If there's a difference that is small, 0.1 to 0.4, we label that non-polar covalent. If we have a difference of 0.5 to 1.9, we have a polar covalent. 2.0 or greater is now classified as ionic, where we have a complete transfer. So, on a scale of electronegativity difference, a pure covalent where we have 100% equal sharing has an electronegativity value of 0. Between 0 and 0.4, we call this nonpolar. Between 0.4 and just under 2%, we call this polar covalent. And anything larger than that would be known as a complete ionic transfer, known as ionic bond. A nice difference here is 2.0 is the cutoff between covalent and ionic, knowing that we have a nonpolar bond when those numbers are very close to 0, polar covalent with 0.4 up to 0.2. And to find these, it's as simple as subtracting from our chart. If we'd like to know